All right. My name's Conrad Cardano, and I've been a member of Skyscrapers for decades. I don't even remember how long it is. I do have an observatory. I live on Dye Hill Road, so I call it Dye Hill Observatory. It's a Tupperware shed that I converted it into an observatory, and the roof folds off. It's really nice. The goals for this meeting. I want to give you an introduction to astrophotography. Everybody has to start somewhere, and I did a long time ago. Um, when I started, actually, it was back in the 70s doing film astrophotography. And there's nothing more difficult in this world than film astrophotography. And I'm glad we have digital cameras. You take your pictures, you send them off to a drugstore to get them developed, you get them back, and you find that maybe only one of them is any good. Uh, so I'm going to encourage you to try it. It's a lot easier now, and you don't have to spend a fortune. And one of the nice things, this is the wall in my office. You take pictures. Um, I get them enlarged at Walgreens. It's not expensive. They look good. And consequently, the whole office looks really good. Oh, and before I get too far ahead, if you have any questions, your questions are always welcome. Please ask them. Resources. 20 years ago, there weren't as many resources as there are now, but there are so many things out there. For example, YouTube, if you just Google on beginning just type in and search beginning astrophotography, so many things will come up. And there's a lot of videos out there, people doing all types of astrophotography, and you can learn a lot from it. And another place that has a lot of information, Agena Astro Products. Of course, they want to sell you stuff, but they do have a lot of nice information on filters, cameras, mounts. A lot of these retail websites have a lot of very good
I don't
information.
know. Oh no.
What kinds of astrophotography are there? Well, the first one is nightscapes. And this one of Hale Bopp I just took with a film camera using Ektachrome film. Okay, somebody needs to mute their microphone out there. Okay, this was taken in the days of film photography, and this was just a camera on a tripod, nothing fancy. In my backyard in Coventry, I set up a Canon digital camera with a 50 millimeter lens. Take a little 15-second exposure, and I've got the Andromeda Galaxy on there. One thing I'm really impressed with is in the back of Sky and Telescope, there's always great photographs in there, and people have um, put in there some absolutely gorgeous and creative nightscapes. So you could do things like that with practice. Lunar and planetary photography. Lunar photography is easy because the moon is so bright. You could actually do it with a Dobsonian telescope and no motor mount because the moon is that bright. And once you start taking pictures of the moon, you're going to be quite surprised with it. Planets are not that difficult. This was taken with the Meade 16-inch at Seagrave. A lot of nice detail in there. And hopefully, maybe you could use that scope sometime in the future. Deep sky. These are the ones that everybody sees in sky and telescope and they love. But I took these in my yard and I didn't use a huge telescope. Here's good old Orion Nebula and M31. Okay, This one you just have to do once in your life because it's always so spectacular looking. This was not taken with a big telescope. It was taken with a 3-inch refractor, okay? A 3-inch f6 Astrotech refractor, not an expensive telescope. And I used a digital camera, and you can get great results like this, but you do need a motorized mount. Okay, let's go into part one. I want to talk about the types of cameras. And very importantly, I need to talk about the sensor. When you look at cameras on the retail sellers' websites, you could get very confused because there's so many things there. And something that's very important that you may not think about, it's called field of view. You have a camera, you have a telescope, but what can you really photograph with it? Because there's a relationship between the two. So let's talk about the type of cameras. You can have a digital single lens reflex, which I refer to as the DSLR. Canon and Nikon are the two big ones. You can adapt them to hook them onto your telescope. Interesting. Smartphones. I see more of this coming up. More ways to attach a smartphone to a camera. I remember at Seagrave Observatory, one little girl with a smartphone, when we were looking at the moon, she came up with her smartphone and took a picture of it. And also the dedicated astro cameras. You have companies like ZWO, QHY. Those are two big ones, and they make very good cameras. Okay, this is my Canon camera, Rebel TI1. I must have bought this 10 years ago. It's got a large color sensor, which is really nice. It's 15 megapixels. Here's the sensor in it. It's 22 millimeters by 15 millimeters. Now, these are designed for terrestrial use. You can use them for astrophotography. That works out well. Okay, if you're going to hook them up to your telescope, you're going to need some connectors to it. You're going to take the lens off and you're going to look for something called a T-ring. Now, on this one, this is a picture of one that connects to my Canon camera. This has a bayonet type mount to it. You take the lens off, you connect that in there. And then you notice the little screw fittings in here. I can take this 1.25 inch, it's called the T-mount adapter. I can screw that in here, and this will then go inside the eyepiece holder for a telescope. Here's an example of my camera with, this is the T-ring and the adapter on that, and I can hook it up into a telescope. There's a few things you have to keep in mind. This is the eyepiece holder on a Newtonian telescope, and typically most Newtonian scopes may not have enough eyepiece travel to accommodate your camera, something like this. They won't rack in far enough so that the image touches the sensor. However, they do make uh, Newtonian telescopes specifically for imaging, and some of them are not very expensive. And another thing that you could do with this, I've done in the past, is you could put a Barlow lens in here and it will push the image out onto the image plane of the camera. Refracting telescopes usually have enough travel. This is my Canon camera connected to my 3-inch Astrotech. And this is the scenario that I used when I took the picture of the Andromeda Nebula. Smartphone adapters, they're very clever. And but there is something I have to say about smartphones. You can buy a cheap one or you could buy a very expensive one. I own a cheap one. Okay. I don't use it for astrophotography. And the expensive ones put out some really great images. There are connectors that will let you connect it to the eyepiece of the scope. Because one thing I've noticed, if you try and hold it over the eyepiece, it's not easy to do. So if you really want to do that, you're going to need one of these contraptions. And also something that's very nice, some of them have Bluetooth remote controls. So you don't have to touch the button to take the picture. These are some of the examples that I've seen on the web of people using smartphones. This isn't bad. I mean, obviously, here's the Andromeda Galaxy. Here's M32. You see a little bit of the dark lanes. This is not a fantastic photo, but it's not bad. And the moon is so easy, it's hard to go wrong with it. It still looks great. The dedicated astro cameras, these are great. But something to point out is they're going to need what I call capture software, and you're going to need a computer. And looking at different websites, on one of them, I counted over 200 dedicated astro cameras for sale from SBIG, QHY, you've got ATIC, ZWO. This one is, I don't remember the name of it, very expensive. But the prices can go anywhere from $150 to $125,000. Yeah, it's confusing when you see 200 cameras out there. But something that's worth remembering is that there's two big sensor manufacturers. You have Sony, they make complementary metal oxide semiconductors, and Kodak, which makes CCDs. Now, I put these asterisks here because Kodak is getting out of the business of making CCD chips. There's been such an improvement in CMOS chips. They're not only better, but they're cheaper. And all of the cameras coming out now are using CMOS chips. Different camera makers, okay, QHY, ZWO, they're all using the same sensors. An example is you might have a QHY 462C and the ZWO 462MC. It's the same chip. They may put a few different bells and whistles on it. And it's also worth noting that an expensive camera it's not a guarantee of great results. It's all in the mount, the image processing, and something that isn't said very often, sky conditions. Okay. If you have a lot of turbulence in your skies, yeah, there's not much you can really do. A lot of light pollution. Another thing that you're going to see out there are cooled cameras. They have built-in cooling units. Okay. And what this does, it reduces thermal noise. The heat can actually trigger electrons in the little camera sensor. So your readings may not always be just photons going in. They could be heat. On hot days, this could make a big difference. So the cooling units improve the image on a hot night, but they do add some additional costs to the camera. And in the cooled camera that I have, uh, it was an additional $400, but I think it was worth it because I do astronomy during the day. Okay, before I go any further, does anybody have a question? Okay, doesn't sound like it. Now, when I talk about the sensor chip, I might stop the screen share because I made some little demonstration things to illustrate certain points, and then I'll get back to this PowerPoint demonstration. Okay, the chip type. All right, we have CCDs and CMOS chips, and they look the same. And for many years, CCD chips were better than CMOS chips. They both converted light to electrons, but CCD chips were always more expensive. But the strange thing is that CCD chips were noisier. And if you don't understand what that means, I'll explain it later on. And CMOS chips getting better, they're going to have a lot less noise. CMOS cameras are the best buy for the money. And due to improvements in CMOS sensors, CCDs are no longer being produced. Pixels. Okay, you take that little sensor that's in the camera and you magnify it, and it looks like a big rectangular grid where each little rectangle in here is a pixel. And a pixel is just a tiny light sensor. And it's going to capture photons and it converts them into electrical signals, okay, that come out and get displayed somewhere. Now, I am going to stop sharing my screen just for a moment. And can everybody see me on there? I hope so. All right.
Yes.
Yes. Okay, good. Because, you know, what I was going to do tonight, if we were at Seagrave Observatory, as an analogy, I was going to use Dixie cups to illustrate some important points about pixels. You can have little pixels and you can have very big pixels. Okay. And another feature here, and this took me a little while to do. If you look at it, this is my array of Dixie cups that I'll talk about later on. And this is going to be my pseudo camera sensor. And I'll use this later on. This is an array. It's 6 Dixie cups down and 7 Dixie cups over. So it has a total size of 42 Dixie cups. Okay. So we'll get back to that later on, but I am going to share my screen again and we will go back to the presentation. Oops. Okay. Pixels. Let's go on to the next thing. One thing that you're going to see, color chips, monochrome chips. Okay, with the monochrome chip, all of the colors are treated the same. Red, green, and blue light's going to go into this little square and they all get added up. All colors get treated the same. Color chips are different. I don't know how they do it, but it's pretty amazing. Each pixel has either a red, a green, or a blue filter in front of it. That's pretty amazing. If you take a little magnified view, it's going to look something like this. Now, this represents 4 pixels. Okay, I want you to keep that in mind. The combination of these 4 pixels make up a single color pixel. Okay, so depending on how much red and green or blue you have, you might get magenta, you might get pink, you might get orange, you'll get something like that. Something that's worth noting that the resolution on a color camera is going to be less than that for a monochrome camera because it takes 4 pixels to give you the one color. On this chip, whoops, didn't mean to do that. Uh, 4 pixels are just 4 pixels. Each one gathers light and you get higher resolution. Okay, let's talk about the size of the pixels. Okay, here's an array of, let's say, 960 pixels in the vertical direction and 1,260 pixels in the horizontal direction. You multiply those two together, and it's pretty amazing that you have 1.2 million pixels on this little sensor that's no bigger than a postage stamp or smaller. The size is measured in megapixels, so this would be a 1.2 megapixel array. They can go anywhere from less than 1 megapixel to 100 megapixels. 100 megapixels is really nice, but each image could be huge. It could just take up a lot of room on your computer in no time at all. The pixel size, okay, it's measured in microns. You're going to see that out there, and you'll see this little symbol. Looks like a U. Okay, 1 micron equals 1,000th of a millimeter. And dimensions, it could go anywhere from 2.3 microns. I've seen them now that are less than 2 microns with some of the very new cameras. Could go all the way up to 9 microns. Okay, this is a really important point. Each pixel is like a bucket. When it's full, it stops collecting. No more. That's it. If you have a monochrome camera, when it's full, that pixel is white. Okay. The pixels around it may not be full. Okay. So they're still collecting photons, but that one pixel that's full, it's all done. So you will see the term well capacity, how much light the pixel can absorb. And you'll see values anywhere from like 5,000 electrons to over 63,000 electrons. That would be a big well. You could have a long exposure with something like that. This might fill up very quickly. All right, let me do a little demonstration. So I'm going to stop sharing my screen for a bit. All right.
Conrad, I have a
And
question.
okay.
Does well capacity have anything to do with how many microns size the pixels are?
No. Although, okay, not indirectly in a way, I should say yes. Okay. Again, I'm going to go back to this Dixie cup again. All right. This Dixie cup may be that 5,000 electron well capacity. This one could be the 64,000 uh, electron well capacity. The big pixels are designed to gather lots of electrons. Okay. I have seen cameras out there where the pixels might be not 2 microns, but they might be 4 or 5, and they may have a well capacity of like 20,000 electrons. So, in a way, there may be a relationship between the two. And one thing I've also noticed, the big pixel cameras are used very popular with deep sky astrophotography. And the little ones are very good with lunar, planets, and solar astronomy. I'm going to go back to,
Conrad.
where are
Yeah,
you? Okay, Greg,
right
there
here.
you are.
Uh, now, I can attest to that. I do a lot of planetary imaging, and the smaller the micron, the larger your planet will be for the same aperture that you're
Right.
using. So most of my ZWO cameras are 2.9 microns, and I have 178 mm, which is a 2.4 micron. So it's half a micron less,
Yeah.
2.4 as opposed to 2.9. And what a difference. I can see the planet is that much bigger. You measure the circumference of
Right.
pi r squared. It's a lot bigger just because the pixels are smaller and the planet's a bright object, so you don't need large pixels like for deep sky. Even Uranus and Neptune that are, sixth and eighth magnitude are still brighter than, things you're imaging at,
Right.
15th magnitude,
Yeah.
deep sky. So, and then another thing too is I learned from Crisco, who's a uh, premier planetary imager. Do not use, he tried using a cooled camera for planetary
Right.
because, he lives in the Philippines. I live in Florida now, so it's very hot and humid there. So the chip, it says the temperature and it's usually 95 to 100
Yeah.
degrees, so it's very, very hot. So he tried using a cooled camera and he said, since you're in high power, you're getting vibrations from the
Yeah.
camera. So with deep sky, that's not an issue because you're wide field. But with planetary, even though it may be hot, you don't want to use a cooled camera. So that's a good FYI because those are a lot more expensive than cool cameras. So save your money, just get it uncooled for
Yeah.
planetary.
What I've seen, and I've seen it on YouTube videos, people are complaining about the fans on cooled cameras,
Oh,
adding little vibrations. So if you're trying to get tremendous detail, you may not get it because of those little vibrations.
right. In deep sky or
No, this
planetary?
is for planetary stuff.
Yeah, for planetary. Yeah, yeah. So that's a big deal. So save your money. Don't get a cooled camera for
Okay.
planetary. Okay, that's all I have. Thank you.
Okay. All right. Let's continue. Let's talk about bit depth. Okay. Light goes into the pixel, and then the electronics are going to read the pixel, and out comes a number. And you get millions of numbers from an array. The bit depth is the possible range of numbers that's going to come out of that pixel. If you have an 8-bit camera, the number that comes out is going to be a number from 0 to 256 for each pixel. However, if you have a 16-bit camera, could be anywhere from 0 to 65,000 for each pixel. Does that make a difference? Yes, it does. Okay. For an 8-bit camera, between black and white, you're going to get 256 steps. For a 16-bit camera, you're going to go have from 0 to 665,000. There's going to be that many steps in between the two. So you get your image is going to be smoother and it will look better. I don't see 8-bit cameras anymore. A lot of the cameras I see out there for sale are 12-bit, 14-bit. So there's been a lot of improvement. And 12 and 14-bit cameras are very good. Okay, binning. Okay, you will see that with a lot of the cameras. And what they're doing is they're combining adjacent pixels to make a super pixel. So if you have bin 1, it's just 1 pixel. If you set your camera to bin 2, okay, you're now going to take 4 pixels and you combine the signals together, you get a higher signal. And bin 3, which I've never used, you're going to be combining the signal from 9 pixels. It increases the signal quite a bit, but your resolution decreases. Which is better, color or black and white? Color's pretty. Color is very pretty. A lot of the pictures you see in Sky and Telescope, beautiful color pictures. But from my own experience, color is much harder to process. You have things like white balance, hue and saturation, and you have red, green, and blue colors that have to be mixed just right. And I got a great example here. Okay, this is Barnard's Loop. This is constellation Orion. Here's M42, the Orion Nebula. Here's the belt, the sword. What's actually in here is the Horsehead Nebula. But Barnard's Loop is this nebula that goes through here. Now, I took this with a Canon camera and I had a 50 millimeter lens on it. And I spent days trying to get these colors to balance right because it just doesn't look right. You change one color to try and make it look better, and all of a sudden something else pops up. Uh, it's not easy, but something like the Orion Nebula, which doesn't have all these colors, was a lot easier to do. From my own experience, most of the things I've done are black and white, just because getting that color right is never easy. But I don't want to discourage you from trying color. If you have a digital single lens reflex, which is color camera, use it, try it. Noise, electrons in your signal, but they don't come from light. Okay, light hits the pixel, but you've got two things, electrons from the light and electrons from heat. Heat is a form of energy which can stimulate the release of electrons in your pixel. They go through the electronics and out comes a number. And that number is the sum of light plus heat. Okay, it is measured in electrons per pixel. For example, 1.2 electrons per pixel. Lower is better. The good news is cameras keep getting better and better, and this number keeps getting lower and lower. 20 years ago, this number might have been 20. Okay, these electrons from heat are generated even in total darkness. Warmer temperatures generate more noise, but cameras can be cooled to counter the effect. And another thing that's very important to know, and we'll talk about it and I'll give you examples, this effect of electrons not from light can be removed using something called dark frames. Okay, before I go and talk about field of view, does anybody have any questions? Okay. Here's a picture of the sky, but with different lenses. Here's a nice 50 millimeter lens. You get a great view of the Milky Way. 70 millimeter, you're going to get magnification. 200 millimeter, you're going to just start zeroing in right on the Trifid Nebula. Two factors in this calculation, the size of the sensor and the focal length of the scope. There's a very simple calculation, and I'll show you the consequences of it. Okay, the first number we need to find out is the size of the sensor. So we could just measure along this direction, all right, of this rectangle. And let's just take, for example, that it's 4.8 millimeters, and we're going to call that D. And the next thing is the focal length of the telescope. If you own a Celestron C8, it's got a focal length of a little over 2,000 millimeters, and we're going to call that L. And the formula is just take the 3400, we're going to multiply it by D, and then we're going to divide it by L. And this gives the field of view in arc minutes for the telescope and camera. So in this example, 3,400, 4.8 divided by 2,032, we can see 8 arc minutes of the sky. With 8 arc minutes of the sky, what can we image? Well, the planet Jupiter is about 1 arc minute, so that's going to be fine. The Ring Nebula is 3 arc minutes, so that's going to fill up a lot of the sensor. This is M51, the Whirlpool Nebula. It's too big. It's going to overflow, and you're only going to get a piece of it. The moon is 30 arc minutes. If you just want to take pictures of the craters, that will work, but you can't get the full moon in there. If you tried to take a picture of the Andromeda galaxy, you're only going to get a little bit. Let's try something different and let's change the scope. We'll use the same camera. I'm going to use that 70 millimeter, almost 3 inches, f6 refractor. It's got a focal length of 420 millimeters. Okay, that's a lot less. It's about 1/5. We're going to use the same formula, and we're going to find out with this combination, okay, with the shorter focal length, we get 39 arc minutes of sky. What can we image? Jupiter's not going to look very good. It's going to look like a little dot. The Ring Nebula is going to be very small. The Whirlpool Nebula is going to look very good in there. You can get the moon in there, but it's not enough if you want to get the Andromeda galaxy in there. All right, this time let's change the camera. Suppose I use that DSLR with the 22 millimeter chip. Use my Astrotech 420 millimeters. Same formula. And when we put the numbers in there, I'm going to get 178 arc minutes. Okay, that's almost 3 degrees. What can we image? Planets are going to look teeny tiny. The Whirlpool Nebula will fit in there, but it's going to be small. You can get the moon in there. It's going to be small, but the Andromeda Nebula is going to look great. So as a guide, planets and planetary nebulas, you're going to need a telescope with a long focal length, or you could use a Barlow lens on your telescope. If you've got a globular star cluster or small galaxies, you probably won't have to do anything. Okay, your scope is probably going to be good enough. But if you get something big, okay, galaxies can be large, nebulas can be large. So you have a telescope with a short focal length, or you could get a focal reducers. You'll see a lot of those out there. And you could always get a camera with a big sensor. Okay. So for beginners, if you have a digital single lens reflex, try using that. If you already own it, just get the parts so you can connect it to your telescope. I would advise that you get a remote control. That way you never have to touch the camera. And if you want to buy an Astro camera, starting off, expect to pay about $150. I recommend monochrome. Okay, that way you don't have to worry about colors. And it will probably be about 1.2 megapixels. Color cameras cost less, although getting that color right can be difficult. And depending on what type of a telescope you have, you could get a focal reducer or a Barlow lens to help you out with it. Does anybody have any questions? Okay, let's go on.
Would you explain about what a Barlow lens is and what
Okay,
it
a
does?
Barlow lens is a multiplier lens that you would attach your, you can put an eyepiece in there if you want to double the magnification, or you can attach it to a camera. And what it does, it acts as though it's increasing the focal length of your telescope. So if you have a telescope with 1,000 millimeter focal length and you put a Barlow lens on it, that's multiplies 2x, then all of a sudden your telescope behaves as if it were a 2,000 millimeter focal length
So
telescope.
it's like a teleconverter in photography.
Exactly. Exactly. Any other questions? Okay. Part two, the mount, the mount. I have looked on the web, and for good astrophotography, one thing they emphasize a lot is the mount, and you'll see why. Talk a little bit about computers and some techniques used in astrophotography. Okay, why is a mount important? Okay, this is what you get with a good mount. You get a little gust of wind, and all of a sudden it looks like this, and you've just been wasting your time. Um, with a camera on a tripod, and that's how you're going to get these nice nightscapes. Okay, the remote control is handy. Okay, with tripods, a cheap tripod, I don't recommend it. You're going to get what you pay for. The biggest problem I found with a cheap tripod, and I know because I own one, is that the lens being heavy just makes the camera sag. The whole tripod is just not strong enough to hold the camera. Um, Ironically, I got a fantastic tripod at a thrift store. In fact, they gave it away. They didn't want it anymore because no one bought it. So I brought it home. It was a very expensive tripod. It will easily hold about 6 or 7 pounds. And you might have that kind of luck by going to a thrift shop. The nice thing about a camera on a tripod, it's a portable astrophotography observatory. This is a picture I took of the Grand Canyon of the Milky Way. Just a camera on the tripod, nothing to it. A good tripod makes all the difference. If you have a digital single lens reflex on a tripod, how do you prevent star trails? When it's exposed too long, you get trails instead of nice round stars. Some people like that, but I'm not one. So there's a real simple formula, okay, what the shutter speed should be. 500 divided by the lens focal length multiplied by 1.6. So if you have a 50 millimeter lens, uh, you're going to get an answer of about 6 seconds. Keep your exposure to 6 seconds and you'll have nice round stars. So you could increase the gain of your DSLR to something like 1600 and get good results. There's another thing coming out. There weren't many of them 10 years ago, but I see a lot of them now. They're called camera trackers. It's got a built-in motor. You have to put it on a tripod. It'll support 5 to 10 pounds, so you could have longer exposure, no more star trails, but they can be a little pricey. You're going to put your camera here. You're going to attach it to the tripod, and you can polar align this arrangement and take some nice pictures with your DSLR and a telephoto lens. Oh, but everybody wants those nice pictures of galaxies and clusters and all that stuff. So if you're going to put your camera on a telescope, you're going to want a motorized mount. You may see a lot of things like this. This is an equatorial mounted scope. Okay. One axis of this scope is aligned with Polaris. Okay. And consequently, as the telescope turns with its motor, it's going to follow the stars. So you can take long exposures. The angle is going to correspond to your latitude. And as the Earth turns, the scope will turn with it. Now, mounts are going to cost anywhere from 600 on up. And what influences the cost of the scope is how much weight it can handle. A $600 mount can probably handle 10 to 12 pounds. For a scope like this mount costs about $1,200. If you have a scope that's like 30 pounds or more, you can expect to spend a couple $1,000s on it. Now, you'll see a lot of scopes with mounts like this. These are called alt-azimuth and fork mounts. Okay, you can't polar align these scopes. If you take successive images, the whole field is going to rotate. You may have the object that you want dead center, but all the stars are going to rotate a little bit. Okay, these types of scopes will go in this direction and then they go up and down. Now, I think there is some image processing software that can compensate for the rotation. They will stack successive images and make the correction for it so that you can get a decent image. Computers, laptops are preferable because you can take them outside, and you're going to need a computer to capture images with your dedicated astronomy camera. If you're going to get a PC, it helps to have plenty of memory and plenty of CPU speed. You don't need memory and speed to capture the images, but when you want to process them, you're going to need it. MacBooks are great machines, but there's a limited amount of software out there. For capture software, I know that Fire Capture is out there. That's very good software. There's another product called, I can't pronounce that, but that's what it is. Techniques. Talk a little bit about focusing. How long the exposure, how high the gain, dark frames, flat
Oh,
frames.
Conrad,
Yeah.
one comment I find for the computers, buy a gaming laptop.
Oh, those are great.
MSIs
They have
are
everything.
excellent because they'll have higher order, that they'll have, the best motherboards and screens,
They're
and
built for speed.
they're built for speed, exactly. And like you said, for processing, especially planetary that I do, you're waiting there forever with the MSI and other gaming computers. It goes much faster.
Right. One thing I want to give as a suggestion, um, I don't buy brand new computers. I've got three of them here, and I bought them from Dell, and they're all refurbished. And I've gotten great deals on them. They cost a lot less. And the computer that I have right now that I'm showing this PowerPoint on was 12 gig, and it's got an i7 core chip. It's fast and it cost a lot less than if it were brand new, and I've never had a problem with it. Focusing, the difference between a good and bad focus, well, you can have a fuzzy image or you can have a nice sharp image. Okay, with how to get a good focus with your DSLR, well, what I did for several years was that I just look at the screen on the back of it and I would eyeball it. I could magnify the image on here by manipulating some of these buttons and then rack the eyepiece in and out until I got just what I needed. And that worked. Okay. My DSLR came with software that displays the image on a PC, and that was really nice. Another thing that's very useful for a telescope, something called a Batinoff mask, and I've used it several times, and they're great. It goes on the front of your telescope, and you get a series of spikes and the image of the star, and it shifts position during focusing. So inside focus, it's not aligned. Outside the focus, it's still not aligned, but perfect focus, everything's in alignment, and it's very easy to do. If you have a dedicated astro camera, Capture software has a live view to help you focus on stars and planets. So you can get a picture of the planet, and as you change the focus, you'll see it right there live on the screen. Which is better, one long exposure or many short ones? So long exposures are harder, something bigger than a minute. And poor polar alignment produces blobs instead of stars. And the worst part of it is lines may appear from planes and satellites. Now, these are my photos. Okay. Lots of times they're just ruined. Here's the Helix Nebula, ruined because something came in there. This image of Hale Bopp, here's a plane going off toward Warwick Airport. And this was a plane going somewhere else. And one thing I've noticed more and more, I see more satellites in the sky now than I ever have. So a shorter exposure might help you prevent that. So my recommendation is to take short exposures. The processing can stack these images. So 20, 30-second exposures can stack up and give you the same results as one 10-minute exposure. So as a guide, well, planets are going to take short exposures, and that's fine. You know, that's easy to do, and you can stack them up. And galaxies, you're going to take longer exposures, 30 seconds possibly. Okay, here's an important thing, camera gain. You can make your camera much more sensitive by fiddling with the gain. Okay, changing the camera gain changes the saturation point of the pixel. Low gain is low sensitivity, high gain is high sensitivity, but you get grainy results. Okay, what I'm going to do is I'm going to stop sharing for a moment. Okay, and I am going to go back to one of my little demonstrations here. All right. Okay, here's my Dixie cups again. Suppose this Dixie cup, okay, can hold 5,000 electrons. If I change the gain on that, let's say I move it up quite a bit, instead of becoming full on 5,000 electrons, it might get full on 2,500 electrons. Okay. Oh, and going back to my array, all these Dixie cups here. All right. If I change the gain on it, okay, and I pick, let's say, one of these cups in the middle, this is going to fill up real fast and just be white. But the cups around it are still filling up. Okay. This could be your black, and that one in the center could be that one full pixel. But all the cups around here is going to be gathering electrons and photons, and it's going to ruin the contrast. That's why high gain is not a good thing. Let's see. Let's go back to sharing the screen. And let's go back down. Okay. Oh, all right. Camera gain. So changing the camera gain changes the saturation point. That pixel is going to fill up much more quickly than before. All right. But once that pixel is full, the other pixels around it are still going to be gathering photons because they're not full yet. So your contrast isn't going to look right. A DSLR, you can play with the ISO number. I've used an ISO of 1600 and had good results. But if I go to 3200 or 6400 as an ISO number, it's not that good. With the dedicated Astro cameras, it's going to be software controlled, and it may be a number from 0 to 1,000. But you want to look at what the manufacturer stats have. A dark frame. As I said earlier, camera sensors records electrons even in total darkness. So what you'll do is you're going to take an additional image with the scope covered, same exposure time. And this is going to be your dark frame. And your processing software is going to use that. Oops. Okay, so during the image processing, the software subtracts the dark frame from the regular frame. And does it make a difference? Here's a good example. Here's the raw image from the camera. And this is what the dark frame looked like. The telescope was covered. Okay, so I had my camera take a picture for 30 seconds, and this is what I got. This is what they call amp glow. This is internally from the camera. And you get some brightness along here because some electrons are being released from the heat, or I should say by the heat. And the software is going to subtract this image from this image. And this is what you end up with. This is a totally different image. It looks much better. What's a flat frame? Okay, you're going to see that term out there too. Okay, it's an image that you're going to take that shows the light distribution across the chip. It's going to show the sensitivity of each pixel, and it shows, and this is the great part, just on the sensor. Okay, this here, this monstrosity is an image, okay, of the daytime sky with a t-shirt covering the front of my scope. And as you can see, it is not uniformly lit. These donuts, that's dust on the sensor. And that's why it's helpful to have a can of compressed air around. Now also notice how these edge portions are dark. Okay, that's called vignetting. Okay, you're having your round telescope objective put an image on your nice rectangular sensor. So usually there's a fall off on here. So you will want to take a flat frame. So during this day, you're going to cover the scope with a white cloth away from the sun. You take an exposure, and your capture software can help you do it. Sharp Cap is very good. Okay, we'll talk a little bit about Sharp Cap. That's great software to help you do that. And that's going to be your flat frame. And during image processing, the software divides the image by the flat frame. Okay, so here's an image minus the dark. And here's the flat frame. Your software is going to divide this by this. And this is what you're left with. Okay, this image is a little better. It's still not perfect, but it's an improvement. Guiding. You'll see a lot of people out there doing guiding. And these photos were taken with a polar line, motorized equatorial mount without a guider. Okay, this was taken on the 16-inch Meade, and this was taken on my 6-inch reflector on a Celestron AVX, no guider. Okay, you could still get good images, but you got to make sure that it's polar aligned. Okay, no special guiding was done in this photo, just to convince you that it can be done. I've got 94 30-second exposures, and the image processing software corrected for any little imperfections in guiding. And this is what I ended up with, which is pretty good. With guiding, you'll have a guide scope. You've got 2 telescopes and 2 cameras on the mount. Your main telescope, and then this little guy is your guide scope. And you're going to have a guide camera. They're going to be connected to a computer, and you're going to have guiding software. And this guiding software sends signals to the mount to make little corrections. Probably the best one out there is called PhD2, and it's free. The PhD stands for Push Here Dummy. It's been around a long time, and a lot of people use it. This is certainly a much more complicated situation because you got 2 cameras, 2 scopes, and a lot more software. And you have to make sure that your mount has a plug so you can connect to it. Okay, file types and software. Okay, when you look at cameras, they're going to talk about JPEGs and FITs and RAW and all kinds of things. And you're going to need a little help to figure that out. And we'll talk about software to capture images, software for image processing, free versus the money software. There's some good free software out there. Again, these are all the different types of images, AVIs, PNG, TIFF. You're going to see all this and you're going to get confused. What does it mean? But there's basically 2 types. We've got single frames and you got videos. Okay, I do take videos. Okay, for single frame, you've got your RAW, which is associated with your DSLR, FITs, TIFF, PNG, and JPEGs. Okay, FITs is an uncompressed image. Okay, it has the most amount of information in there, and this will be your biggest image. Some of these are going to have some compression in there, so they're going to get smaller. And JPEG will have much more compression in there. A lot of pictures that you'll see out there will be JPEGs. With videos, you have 2 main ones, SCR, which will give you 16-bit images, and AVIs, which will give you 8-bit images. With my DSLR, my camera can save images 2 ways. RAW, which each image is 15 to 20 megabytes, no compression, maximum resolution, or JPEGs. Okay. Images are compressed, save space. Some fine detail will be lost. And I have an example of that. This is a RAW format, and this is a JPEG format. Okay, this is definitely much sharper, has a lot more detail than this. Dedicated astro cameras. Full uncompressed images. Now, this is just a picture of my camera. It can produce a 46 megapixel 14-bit FITS image. Okay, what does FITS stand for? Flexible Image Transport System. Why does this even exist? These are very useful, this type of a format, because each image has a header on it, and you can store information in the header. You could put latitude, longitude, the time of exposure, your name, the name of your observatory, all kinds of things can go in there, which is really very useful. When I send images to the AAVSO, they want this information. But you need imaging software to view a FITS image. This camera, if I want, will produce compressed images. JPEG, which is just an 8-bit image format, or TIFF, or PNG. TIF is tagged image format. PNG is portable network graphics. I've looked at them both. I can't tell the difference. Video formats, this camera can do AVI 8-bit, SCR 8 and 16-bit. 16-bit is very useful for the format, for the higher resolution when I do my solar imaging. Capture software, DSLR, and dedicated astro
Conrad,
camera.
I have a
Yes,
question
yes.
regarding TIFF and PNG. I noticed that I like saving in TIFF and the files are like 1.5 megabytes. Then if I save the same file as PNG, it's like 300 kilobytes. I mean, why is this so tiny? Is it saving all the information as a PNG? Why is the
Um,
TIFF so much more
well, I know you can have
larger
16-bit
files?
TIFF and 16 and 8-bit TIFF and
Yeah,
16-bit and 8-bit PNG. So I'd have to look
yeah.
at the software to see exactly how it's doing it.
Yeah,
But
well,
most,
it's the same picture. So if it's 8-bit TIFF, 8-bit PNG, the file size is just so it's only a few hundred kilobytes in PNG, but it's in the megabytes. It's 1.5, 2 megabytes in TIFF. I always save it in TIFF because I want the larger, it's not really
well,
that much
yeah, you don't
gigabytes.
want any compression on it. You want to save every piece of
Yeah, I don't
information
want any
in that image.
compression. And I know PNG is not compressed, but why are the file sizes so tiny compared to TIFF?
I don't know. That one I
That's
don't know.
that's
Um, if you have a
okay.
DLSR, your camera came with lots of free software, as did mine. And this was one thing that I liked about. Uh, on my computer, I can have a live view window and I can control the whole camera from the computer. Here's the shutter button. I can change the exposure. I can change the ISO. I can change resolution, all kinds of things. I can enlarge this image and just keep taking pictures. Sharp Cap. I use Sharp Cap. I think it's for free software, it's really good. Now, I have the Sharp Cap Pro version, which costs me $10 a year, and I think it's the best 10 bucks I ever spent. And there are great YouTube videos to demonstrate how to use Sharp Cap. Lots of features on it. And they're going to be coming out with a new release pretty soon. Fire Capture is another good piece of free software that people like to use out there. There are also great YouTube videos. They're both free. Download them and try them. You have nothing to lose. This is for Sharp Cap, and this is for Fire Capture. And they have a feature that I like, especially if you want to learn something. In Sharp Cap, it's test camera 1, test camera 2. Okay, it creates this fake camera. It puts an image out there and you can change the controls on it. So you can learn how to use the software. In Fire Capture, it has something called the dummy cam, which you can do the exact same thing. So you can learn how to use the software. Stacking software. You know, after you take your pictures, you're going to want to stack them. You're going to want to enhance them. For planets, moon, and the sun, these are the two biggies. And a lot of people are using them. I prefer auto stackered. It's very easy to use, and I do like it. Nebulous, star clusters, and galaxies, deep sky stacker. And this is a newer thing called Cirrus. A big complaint is a lack of good documentation that comes with them. But if you want to learn how to use it, check your YouTube. There's lots of learning videos on YouTube. This is interesting. This is a 45-second video right here of Saturn. And you can see, you know, it's not always sharp. Sometimes it gets a little blurred. But when you take this 45-second video and you process it with Registax, this is what comes out. Big improvement. You can see Cassini's division. You can see much more detail on it than before. Registax is good software. Okay, I've got this 264 frame video of the moon, and I processed it with Auto Stacker, which I think is easier to use. And the single stacked image, I think, is great. It takes these 264 frames and it evaluates each one and it takes the best ones out and you can tell them how many frames you want to stack. If you enlarge this, you're going to be amazed at the detail that's in there. Deep Sky Stack.
Conrad,
Yes.
what video settings do you use for the planets? What
For the
frame rate? What?
Well, the frame rate that I use when I use Sharp Cap, okay, I'll tell you what, let me go back a bit. Let's see, go back to Sharp Cap. Let's see. Oh, let's see. I got a better idea. All right, I'm going to stop sharing. And I'm going to bring up Sharp Cap. And then I'm going to screen share. Okay. Okay, in Sharp Cap, all right, there's a tool in here called Pixel Value Readout. Okay, let's go to see how this works. Okay, here we go. All right, here's a partial. I don't know what happened, but a partial frame of Jupiter. Okay, what would be the best exposure time for it? Now, they have a tool in here called, let's see, Pixel Value Readout. All right, now I don't know why it is doing this. Okay, you can't see it very well. What it does, it's going to give me a value for how bright that pixel is. Now, I'm going to pick an exposure over here. Okay, so I can have the pixel value somewhere in the middle. Okay, if my camera will allow a minimum value of 0 up to a maximum pixel value rating of, I'm going to make this number up, let's say 20,000. I'm going to adjust my exposure using this tool so that I can have an exposure of like 10,000 so that nothing in there gets overexposed. Okay, does that answer your question?
Well, what if you were using a DSLR or a mirrorless
Okay,
camera?
the best thing to do with a DLSR is to just take a whole bunch of pictures at different settings. For example, if I were taking a picture of the moon, you could use the internal controls of the camera to help you find the best exposure for it. If your camera didn't have that, I would probably take a whole bunch of different pictures at 1/200th of a second, maybe 1/100th of a second, a 60th of a second. Try a whole bunch of different settings to see how well it goes. Does that answer your question?
That
Okay. Let's get back here before we, whoops. All right, we did this one and this one and this one. Okay, the not so free software. This is just a list. There may be others out there. I notice every year somebody comes out with new software for sale. I use AstroArt. I bought it, gosh, 6, 7 years ago, and it met all of my needs. It's from Italy of all places. There's two PhDs out there who put it together, and I thought it was good. I looked around at a bunch of them. Pix Insight, I would say, is probably the number one software out there. A lot of people are using it. There are tons of videos and articles out there on it. There are some other ones. Photoshop is used a lot, but you have to do it on a monthly basis. They're very powerful, all of these, but they have a big learning curve. The best analogy that I can use, it's like learning a foreign language. Once you learn a foreign language, okay, do you really want to go and learn another foreign language? That's why I've stuck with Astro out after all these years. I've put a lot into it. I've learned a lot on how to use it well. And so I want to stick with it. I really don't want to switch to something else. You'll want a fast computer with lots of memory. Minor updates are free, major updates are not free. My last major update for AstroArt cost me $100. There are lots of forums out there and YouTube videos. With the forums, you can post a question and somebody will answer. If you're not sure about something. They're not necessarily cheap, but they have lots of demo versions that are worth looking at if you want to think about buying one. The future. This has been interesting because, 10 years ago, none of this stuff existed. These are telescopes that have a built-in camera, okay? And it sends images to your smartphone or your iPad. This has been out for a couple years, and these have come out lately. And I've seen some YouTube videos on this, and I am impressed. I was at Frosty Drew and I saw one person with a scope like this, and he had his scope pointed at the M33, a galaxy in triangulum, and he had the image appear on his iPad, and I was completely blown away. Much better than anything I could do with my 6-inch reflector. This is called the Dwarf. It's a little telescope camera that's very portable. This is the Sea Star by CWO. It's amazing. Triplet optics, auto tracking, live stacking, Bluetooth connections. You take it out of the bag, you put it on the ground, you turn it on, you get your phone, you connect to it. You have an app on your phone, you tell it what you want to look at, and it will go and take a picture of it. I don't know how anything could be easier. And the results I've seen are pretty good. Okay, these are some of the results. So if you add these things up, instead of a telescope, a mount, imaging camera, guide scopes, computer software, you just have this scope. They're very portable. They were designed to be portable so you could take it anywhere. Results are good. Another neat thing, you could rent a telescope. There are businesses out there who have telescopes in these very dark sites. And I don't mean junk telescopes, I mean high quality scopes. So you could rent it. You pick the object you want to image, and the next day the images are sent to you. And you sort of have like a subscription plan, and you might pay $200 a year. My friend Jeff Padell has a subscription with Slew telescopes, and he got this one image, which is unbelievable, that was taken on a 24-inch plane wave scope, a scope you and I will never own in our lifetime or next lifetime. And he likes to send me the results that he gets from them, and they are excellent. Free telescope time. NASA has a micro observatory robotic telescope network. Looks like this. It's out in the desert, and you log on to this, and they have a list of objects that it's ready to take pictures of the next night. And you tell it what you want to view and how long you want the exposure. And the next day it sends you the results. So I said, hey, there was a supernova in the Pinwheel Galaxy. Let's see if it can capture it. Well, it did. Here it is. It's that little bright spot right here. Here's the Pinwheel Galaxy. Looks really good. It's not very good with the planets. This is the planet Saturn, and so it's not really worth it. So I'm done. And I want to thank all of you, but I would like to, whoops, let's stop the screen share. What I'd like to do right now is invite Mark Muncass. Could you say that? Because I can't pronounce your last name right.
It's Muncasey.
Muncasey. He's
Yeah.
got a few things about scientific photography that he'd like to talk about. So take it away, Mark.
Sure. I wanted to say a few words about scientific imaging. And I use that phrase to distinguish a purpose for going out and doing astrophotography where your objective is getting a measurement from the image that you're taking, compared with say artistic astrophotography, where your objective is getting an image that looks pretty to the human eye, where the human eye is going to do most of the analysis of the image. What can you measure? There's a whole bunch of different things, different measurements you can get out of these images. You can measure star brightness. You can measure star colors. You can measure star positions. People doing work with asteroids, for example, are able to go in and measure the location of the asteroids by measuring the location of the other nearby stars and use that to help track where the asteroids are and whether they present a hazard to the Earth. You can measure the spectra of stars and gather information from that. And what do you use that for? I do projects with high school students, and one of the favorite things that they enjoy doing are looking at exoplanets, where you go in, you stare at a star that has an exoplanet going around it, and if you're staring at the right time over a period of several hours, as the exoplanet passes in front of the star, you get a partial eclipse of that star by the exoplanet, called an exoplanet transit. And you can create graphs of that. You can measure times for that. NASA is begging for people to please go do this because they don't have enough telescopes to monitor all of the known exoplanets. And they really want to gather more timing information on each of those exoplanet orbits. So there's all kinds of interesting scientific imaging that you can do. How is scientific imaging any different from any other kind of imaging? It's really very subtle. 90% of scientific imaging is identical to everything that we've been talking about here this evening. Same cameras, the same need to focus, You're going to gather the same kind of calibration frames, dark frames, flat frames. Guiding is the same issue. What is different, really the one thing that's different, is that with scientific imaging, because you're going to get a measurement out of there, it's important that the entire end-to-end system that you're using stays linear. And what that means is that you want to ensure that none of the pixels that you're going to use in that image have reached the saturation point. And there's really two ways that that can happen. One is in the camera, where due to overexposure or having the gain too high, causing overexposure, where your pixel saturates. So you got to stay away from that. And the other one is in the computer processing that you do of the image after you've grabbed the image, where there's a lot of software for doing astrophotography that does not preserve the natural linearity of the data that came out of the camera. And once your image has gone through some of that software, you can't use that image anymore in that form for getting a measurement. And you have to go back and find some software that's going to maintain that linearity. And then you can get your measurement out of there. And depending upon what you want to do, whether it's measuring brightness, whether it's measuring color, whether it's measuring position of stuff, there are software packages available, many of them free, that will preserve that linearity and help take care of those subtle issues associated with scientific imaging so that you don't have to worry about getting caught up in that. It really is no harder to do scientific imaging than it is to do artistic imaging. And depending upon where your interests are, you may find it very interesting to go off and do that science side of things. I'll also make a plug here for one of the resources available through the AAVSO that anybody can download. The AAVSO has what they call their CCD and CMOS guide to photometry, which is the measurement of star brightness. However, in that guide, there are several chapters that have nothing to do with photometry and instead go into some of the questions that came up here tonight, like how do you read those gain curves that the manufacturers provide? How do you select the right gain for your camera? How do you know whether you're hitting overexposure? How does pixel size affect full well depth? All that kind of stuff is covered there within that guide. So I encourage anybody who's interested in understanding more about their camera to go download that guide from the AAVSO. And if you can't find it there, send me an email. I've got copies of the guide I can send to you. And it's a great reading resource to understand your camera and the process you're going through. Thank you, Conrad. That's it.
Okay, thanks, Mark. Along this line of scientific imaging, just to let you know, this came in the mail within the last 2 weeks. This contraption, this is my new spectroscope. Amongst the many things that I do, I've been doing spectrometry pretty seriously for 8 years now. I started years ago with something called the star analyzer and just keep moving up. And I thought, let's really get into high resolution spectroscopy. Gets to be a lot of fun when you start taking real data and, recording things like gases going around a star and splits in a line. And maybe I'll save that for a future meeting one day. But if there are any other questions, please ask them now.
Yeah, Conrad, regarding the scientific imaging, another thing that I've been doing is taken a lot of planetary images for ALPO, the Association of Lunar and Planetary Observers. The planets are changing all the time on, hour to hour, day to day time scales. So if you look at the clouds of Jupiter changing, Mars will show weather features, clouds will form, and the polar cap gets larger and smaller, and Venus, you can see clouds in the ultraviolet. I even did at the last Alpo conference, I gave a talk on how to go about capturing and processing images of Venus in the ultraviolet. It's on YouTube. So I love doing planetary scientific research because there's a lot going on in the planets as well as the stars and spectroscopy. And also I purchased that ZWO Sea Star. It isn't out yet. It should be out just before Christmas. I can't wait. I can't wait to get that. It is, because I don't like doing deep sky because it's just so complicated, and this thing, like you said, set it up, takes 10-second exposures, aligns and stacks them. I bought a nice new iPad, and then you see it right there. And then you can take it and put it into Photoshop and, make it even better. I mean, deep sky's gotten really easy now, so people will gravitate to it more.
Greg, think of this. You could take that sea star, set it up, and you could do a supernova search with galaxies very easily, because you would easily be able to see that supernova in the Pinwheel galaxy.
Right.
So you could just program it to, every time you go out, take a whole bunch of pictures and keep comparing them.
Right.
See what shows up. Okay. Well, GIMP is freeware. It's free. You can fool around with a lot of the things in there to adjust your image to bring out more features. That's another one. It's very similar to Photoshop. There's going to be a bit of a learning curve to it. Let me see, just a moment. A few other things. Let's see. IMPG. That's another piece of free software out there that will let you do some image processing. And another one is picture in picture. I think it's PIP that I think freeware that will let you fool around with your images, because Photoshop is nice, but a lot of the things that you're working with are they were designed for terrestrial photography and not astrophotography, where you may want to stretch certain features of your image to bring out certain details.
Steps. So I'll look at those. Thank you.